Hello, everyone, and thank you for joining today's webinar. My name is Tyler Mast, and I am the Paper and Board Division Manager, and today's webinar is sponsored by the Papermaking Technology and Operations Committee, the PTOC. This webinar will be held in accordance with TAPI's antitrust policy and procedures. The full policy is available at tapi.org/antitrust. We have a lot of information to share with you today and encourage you to engage with Ben, our speaker, as well as other attendees with your questions and comments. Please feel free to type them into the chat at the bottom of your screen, and we will try to answer all of the questions at the end of the presentation. This webinar will be recorded, and the recording will be available on the TAPI website after this webinar. Let me tell you about our host, Ben. Ben Thorpe holds a bachelor's degree in physics from the University of Maryland and pursued advanced studies in mechanical engineering, management, and marketing. With a distinguished career in the pulp and paper industry, his contributions include innovations in hydrofoils, fab foil system optimization, pulp and paper mill efficiencies, conventional and TAD tissue machine advancements, and pioneering modern forest biorefinery concepts. A TAPI Fellow since 1986, Ben has received multiple industry accolades, including the TAPI Paper and Board Leadership Award and the PIMA Management Excellence Award. He has published over 200 articles, co-authored 2 books, and holds 10 U.S. patents. Now, I would like to turn this webinar over to Ben. Welcome, Ben.
Thank you. And I want to thank my colleagues, Dr. Kachurik, Tom Redensel, and John Ames for helping me with develop this material and peer reviewing it. I also want to thank PTOC for inviting me to do today's webinar. These are some key points that will be made during the presentation. We have found that optimizing Fourdriniers or multi-wire machines, multiple wire machines, is a lost skill. Simple but crucial information is no longer connected, and the design of Fourdrinier tables, one of the things we'll emphasize today is that proper design of Fourdrinier tables is to design first for turbulence and second for drainage. We believe the common practice today is reversed, and therefore some new tables are not optimized. Skill development is needed in the industry. Training should help mills cope with new challenges. And a disclaimer, it is impossible to cram 20, 30, 40 years of industry learning into 30 minutes of slides and 20 minutes of questions. And so the second slide had my contact information where hopefully I can clarify any questions or to discuss unique situations. What is sheet formation? Sheet formation is mass variation, uniformity. One way we look at formation is show through. Hold up a sheet of paper to the light and see the mass uniformity. What we usually see are flocks, that is, clusters of fibers. And we usually are looking at it at the fiber scale, which is 1 to 3 millimeters. When we see these clusters of fibers, which we call flocks, and if you were to be able to pick them out of the sheet of paper and analyze the fiber content, they would typically be softwood dominant. At the center of these blocks, they start with softwood fibers. And the hardwood fibers then cluster around them. There are instruments available for both lightweight and heavyweight sheets, and you can get formation numbers, and they describe various things which the instrument will tell you about. But you can't see through heavyweight sheets. So if you're making a heavyweight sheet, a board grade, uh, coated board in particular, you can't see through the sheet, but there's a trick to being able to do that. And not all mills are aware of this, not all mills do it. But if you'll get a little pan of mineral oil and take your heavyweight sheet and just drop it in the baking dish full of mineral oil and leave it there for a minute or so, the sheet will absorb the mineral oil and become somewhat transparent. You can hang this with a clothespin on a line and let it dip dry, and then put it in a Ziploc bag for show through. So if you got a 12-inch by 12-inch bag, you want to make your sheet 10 by 10 so it fits nicely into the bag. And then you can hold it up to a light and look through it. And while instruments are available, if you're doing work on the machine and you want to know what the formation looks like right away without waiting for your sheet to be sent to a lab and evaluated, this is a very good technique to use during optimization. Here's a picture I found in Mike Kuchurik's material. The right-hand side are softwood fibers, and the left-hand side are hardwood fibers. And while this sheet was formed at very, very low dilution in a tappy sheet standard, you can see the softwood sheet is much less uniform than the hardwood sheet. And the hardwood sheet is going to have billions of more fibers. And formation can also be a topographical issue. On the left, labeled worse, is a sheet where you can see it's not very smooth. And you can imagine that if you look through there, you'd see flocks at all the high points. The right-hand side is a sheet that's been better formed, maybe even in this case going under dandy roll, but there is a topological issue with formation as well as a show-through issue. What are the major drivers of Fourdrinier formation? We'll go over some of the approach flow processes in a minute, but the major drivers are furnish, and retention aid is a detractor, and we'll talk more about that later. The basis weight, the machine speed, and below 1200, it's very hard to get good formation. We'll explain why. Dilution is important, and we can simply think of dilution as head box solids, head box consistency. But the head box usually has mixed fibers, softwood and hardwood in particular. And there's another test that is a little bit more insightful, and that's called the crowding factor. It calculates how close these fibers are to each other, and there's a way to incorporate fiber length in that as well. And we've referenced one of many articles that focus on those issues. And we think this is perhaps a lost skill. Table layout and design is the fourth factor, and dandy roll or Fourdrinier shake or other factors are typically used on very specialty grades and used more on slower speeds than higher speeds because formation is much more difficult on slower speeds. So we're going to go over quickly some hydrofoil fundamentals because we're going to be talking about some things. So we want to make sure we're on the same page. Hydrofoil fundamentals, there have been books written about it, And so this is just going to be very cursory level, but very important. And we'll go over slides 9, 10, and 11 in a minute. But the one principle we want to emphasize is select hydrofoil layout for turbulence. Try and get your turbulence first. I will define turbulence in a moment, and adjust angles to get the drainage. We think that's a lost skill today. Use low vac units. There are several trade names. Don't want to mention any, but they are hydrofoil boxes with either flat blades or hydrofoil blades with very low vacuums and measured in inches of water that are incorporated in these boxes. Use these units at the end of the table to adjust sheet solids going into the dandy roll or suction boxes. Using these kind of boxes upstream or near the head box presents some issues that are very difficult to overcome. This is a slide that's a linear hydrofoil. It's got a doctoring edge, a flat area, and an angle. This one is 2 degrees, and the blade is 2.5 inches long. The scale is vacuum in inches of water, 0 to minus 70 inches of water. And the red line is a foil blade placed in a wet location near the head box, mid table and dry table. And the first thing I would like to point out is that these hydrofoils generate very large vacuums. Talking about 70 inches of water, that's 4 to 5 inches of mercury. That's what an initial flat box might do on the table. So these vacuums are in fact very high, and you're going to get a lot of dewatering with them. 2-degree foil at the end of the table, the peak vacuum is about here. Oops, excuse me. The mid table, it moves down the foil a little bit. It's here. And at the wet end, the vacuum is lower because the volume of water coming out is so great, it inhibits the development of vacuum. So you can get very, very high water removal by going to higher angles, but that may not be what you want early in the table. So that's a principle of how these foil blades work and how much vacuum is generated. And you might ask, well, where does this vacuum come from? Where's the power that causes this vacuum? Down in flat boxes, you have a big centrifugal liquid ring pump or blowers to generate that level of vacuum, but there's nothing attached to the hydrofoil blade. Well, the vacuum is generated by the motion of the forming fabric, and the motion of the forming fabric comes from the couch roll. So this vacuum is actually generated by drive horsepower. And early on in foil development, it was thought that when you put in a table of, say, 40 hydrofoils and replaced, say, 20 table rolls, that you would have much more drag. That turns out not to be the case, but that was some work that had to be done to prove that. This is a blown up diagram exaggerated in the vertical direction to show that the forming fabric changes its shape over these foils. It does not remain flat despite the high tension on the forming fabric or the forming wire. This fabric actually comes down the blade. Remember the other diagram, there was 0 vacuum here. The vacuum is created here at the end. The water is thrust out. Some water is carried over to the next one, but the fabric just changed its angle here. When it changes its angle, that induces turbulence. It changes its angle here. This is a V-type blade. We'll discuss what these are later, but the same motion occurs. And it's this angle that is important in generating turbulence. One consultant, John Ames, has actually measured these things, calculated the vacuums, knows the stiffness of the various wires, and can actually calculate what turbulence various foil shapes and various foil spacings and various speeds will generate. He can actually lay out a table on his computer remote from the mill. These are typical foil blade shapes. The blue one at the top is the standard linear blade, which we saw before. So earlier we saw its vacuum profile. The next is a standard linear blade with an inclined angle going in here. That's to reintroduce water into the sheet to create more turbulence. That's sometimes helpful, but if you do this too much, this incoming water goes back into the sheet, washes the bottom side of the sheet of fines and short fibers, and will create a sheet that has more two-sidedness than a table of these foils. The yellow blade is called a V blade. It has a downward angle. It's going to generate vacuum. The fabric is going to be pulled down, and this surface will cause it to go back very fast, much faster than if the next foil, say 7 inches away, and therefore generate a lot of turbulence. That blade doesn't work as well as the next blade. That's an improvement blade because this dewatering angle back here helps hold the fabric on the flat area and prevents it from going way up. And that then generates a change of velocity, change of angle, and creates a lot more turbulence. So this number 4 blade creates more turbulence than number 2 blade. And if you really want the maximum turbulence available from a hydrofoil blade, you can take this blade and have an ingoing angle. Another way to not have such a steep angle is just to take a wood plane and cut the leading edge of this off and have a sort of a blunt nose. That works, but it also allows fibers to staple on the front nose. And so that's only an emergency procedure that you can use if you need quick turbulence, but are going to change the blade out fairly quickly. Why do we want to improve formation? Well, what we want to do is improve user acceptance. The people that are buying and using the paper want more uniform paper. Better formation can improve printability. It can improve the uniformity of coating. It can improve both tear and tensile strength. You actually get better pressing with a more uniform sheet. So if you get better pressing, you may get better drying. That's going to lower the cost of producing paper. You may be able to run a tad bit finer. Sometimes you can take improved strength and simply lower refining, get lower horsepower usage there, and don't create so many fines in your refining process. Sometimes you can even lower your softwood usage. And since softwood typically costs more than hardwood, you get lower furnish costs. If you're calendaring the sheet, you can perhaps use a lower basis weight and you can reduce the calendaring. One of the things that we're going to talk about is increasing turbulence. We'll define turbulence. But turbulence is a form of shear, liquid shear. You get liquid shear when you stick a knife under a water faucet. Now, water hits the knife and cleans it. That's a shearing action. Where you get shear on a paper machine is in slice geometry. Are you driving the sheet into the fabric, or are you letting it land on the forming board and skate onto the fabric? Then there's the rush drag ratio, the ratio of the speed of the slurry coming out of the head box versus the speed of the wire. The speed of the wire is faster, you're pulling the sheet. If the speed of the fabric is slower, you're rushing the sheet, and they will give you different formations. On slow speed machines, you can use machine shake where the breast roll and the fabric will shake over the hydrofoils. They'll move in and out. Table layout can generate shear, foil design, angles, foil spacings, and the drainage profile can either increase shear or decrease shear. If all else fails, you can use formation showers. They are quite effective. Paper makers, paper machine operators do not like formation showers because, like all showers, they will plug. And when a formation shower plugs, you can get a formation streak and make unsellable, non-sellable paper. So these nozzles have to be cleaned frequently. And finally, you can use dandy rolls. They're also very difficult, and the higher the speed, the more difficult the dandy roll. But those are the tools that we have available to generate shear on the Fourdrinier. We talk about turbulence, and turbulence is what the surface of the sheet looks like. And of course, the sheet is driven by forces that come through the sheet. So turbulence is just a measure of the forces that are being imposed on the sheet. And we could develop a scale. One scale is, if a flat sheet with zero turbulence, it looks glassy, gets a 0. If you can see small little hills, that might be a 2. If these hills look like mountains, that might be a 5. And high turbulence is where there's a little droplet at the end of the spout, but the droplet has not separated yet. Now, when the droplet separates, we get what we call stock jump. And stock jump can be good in that it's much higher turbulence, but it can be bad because these spouts contain fibers. The fiber is going to go up. They're not going to move at the same speed as the wire, so they're going to come back into the sheet at a different spot in which they left the sheet. That's hard to control, so we try and avoid stock jump. This is a photograph from a real machine at 1,800 feet a minute. It was 16 point, very hard to get this kind of turbulence. It was done with the turbo blades that we saw on the previous slide. And we would call this about a 6 turbulence. And these spouts can either be very close together like they are here, or they can be very far apart. And that's the scale of turbulence. So we got intensity of turbulence and scale of turbulence. They're different things caused by different phenomena. We'll describe them both. And the scale of the turbulence is not as important as the intensity of the turbulence in achieving formation. So we've just stated the scale is less important than intensity. A good target number for scale is 40. Now, the way you calculate that number is it's the number of dewatering pulses per second, which is foil spacing in inches divided by machine speed in inches per second. So when you look at the units of what you're doing, you dividing inches per second by inches, and so you get per second or hertz, and a good target number is 40. That'll be hard to achieve because different grades are made at different speeds. This whole thing is described in the Turbulence Approach to Optimizing Fourdrinier Performance, which was published in 1985. That's 40 years ago, and a lot of literature searches don't go back that far. And perhaps this is why there's such a lost skill. Another important issue is the spacing between hydrofoil boxes. On a single hydrofoil box, you can, have 2.5-inch blades, 5-inch spacing. Spacing is the nose to nose measurement. So the box of 5 blades might have 5-inch spacing. And you put a second box behind it, you can get the 5-inch spacing in most cases. You put a third box behind that, and whoops, there's something in the rail. The rail's split, the rail's damaged, and we can't get 5 inches. Today, typically, unfortunately, the practice is, oh, well, let's just get it as close as we can. That's going to hurt the replication of the pulsation of the frequency of the scale. And what you really need to do there is choose a multiple of the spacing in the foil box. If the foil box is 5 inches and you can't set the second box 5 inches from the first box, you want to set it at 10 inches. If you can't do it at 10 inches, set it at 15 inches. And we'll see why that's important later on. We've already covered this. This is a pictorial view of the scale of turbulence. A very coarse scale is where you have very few hills per square foot. Moderate is more per square foot, and a fine scale of turbulence, which is what will help improve formation more, looks like this. So let's go over what happens to the sheet before it gets to the Fourdrinier, because that's critically important. At the furnish stage, when you design the furnish, what somebody is designing for is to get the right ratio of hardwood fibers to softwood fibers to get the right strength. Other additives, wet strength, dry strength resins, other additives, and that's called the furnish. Now, you can pick fibers which are very easy to form, and you can pick fibers which are very hard to form, and that's why furnish is the most critical factor. After we have furnish, we go through refining. Refining maximizes fiber strength and fiber bonding. That gives you additional strength and allows you to maintain or lower your basis weight with the same number of fibers, with the same cost of fibers. And when all that's done, it goes to a blend chest. And the blend chest is simply to get uniform mixing. And typically in the blend chest, you'll have your hardwood line, your softwood line, perhaps some additive lines, and very importantly, your broke line, because all machines have broke. Some have more than others, and that's where it's blended back in, typically at a varying ratio, which can be an issue. From the blend chest, you go to a machine chest. And the purpose of the machine chest is to create MD uniformity. It's not to get more uniform mixing, although some additional mixing will happen there, but its purpose is to create MD uniformity. You may follow that by screening, and that's to remove debris, to get large things out of the sheet, and to prevent machine damage. The purpose of the head box is to create uniform cross-direction delivery up To the machine chest, everything is coming in a nice round pipe, sort of linearly progressing through the process, but you somehow have got to spread this out and get it to your 200, 300, or 400 inch wide machine, and you want very uniform CD delivery. That is exceedingly difficult to achieve. And the head box is going to limit what you can do with your foil table. We'll talk about that a bit more. Again, I want to emphasize the purpose of the Fourdrinier formation. That's first, and dewatering, which is second. Okay, let's talk a little bit about what can hamper formation. Well, furnish is the number one driver. You can have poor forming fibers and low freeness, and that makes formation more difficult. Approach flow piping is a problem because it may not allow the right flow speed. If the speed is too slow, you're going to get more flocking in the fiber, in the sheet. And this approach flow piping can vibrate, and it can transmit hydraulic pulsations to the head box, and in many cases through the head box. So the approach flow piping is not just a transport mechanism, but it's a potential problem area. And finally, we get to the head box. They're important because they can limit dilution. Head box is typically hydraulically controlled. It has hydraulic limits. That means how many gallons per minute will go through the head box and maintain CD uniformity. If you get too low of a flow, you don't get the required turbulence in the head box, and flocks can form and do form in the head box. And if you're not at the right flow rate, you can form so many flocks in the head boxes that it becomes exceedingly difficult to deflock them on the Fourdrinier table. Head boxes may not allow a stable jet. There are some head boxes that I've seen, if you stand on a head box and watch it, especially during startup, when there is no fiber in the sheet will come out, and as the water flow increases, you can look down on the table and see streaks that ebb and flow that are created and that are not there anymore. And you could even see some streaks that move across the machine. Those are head box issues which need to be understood and considered in any table layout. Now, there are also retention aids that are used in most sheets. That's to keep the fines in the sheet. They're beneficial, they do their job, but they can hurt formation. Remember, the retention aids are trying to get fibers to stick to each other. Your turbulence is trying to get fibers to separate from each other. And there's a balance that can be struck, and usually that balance is to minimize the flow of retention aids. Okay, what are some improvement steps? First, you need to understand your machine and your stock prep. You need to understand approach flow for all the reasons we've discussed. Especially need to understand the head box because that's going to limit what you can do. You need to define the resources that are available, and especially machine time. If you're going to have a formation improvement program, we are going to need some machine time. Hopefully you won't make any unsaleable paper, but that possibility occurs and needs to be accounted for in any plan. You may have to shut down the machine and move foil units around on the table, and that's machine downtime, and that needs to be estimated and understood. The most important step is to go back to the blend chest and get samples of the hardwood before it goes into the blend chest, samples of the softwood, samples of the broke, and sometimes you need to get many samples of the broke. There are low flow and high flow conditions. You need them both. And these hand sheets need to be made immediately because if you take a bucket full of hardwood and let it sit in the lab overnight, it's going to flock up and make it very untypical of what you're really dealing with. So you need to take a bucket of hardwood to the lab, have the tappy hand sheet made immediately, take the same bucket back, get the softwood, and especially pay attention to the broke. I personally was involved with one mill. They had allocated a couple $100,000 for a table rebuild because they were having very serious formation issues. Those formation issues tended to ebb and flow a bit, which was an unusual condition. So we took these samples and we found that the incoming broke was not properly deflocked. And no matter what we did on the hydrofoil table, they could have spent the whole $200,000. We could have designed the best hydrofoil table in the world, and it may have helped a little bit, but it wouldn't have solved the problem. The problem was that they had to add more deflocking capability to their hardwood line, um, to their broke, and they needed to control the broke better. And we had to prove that before they spent lots of money on that, and that involved installing a temporary screen prior to the blend chest, so we would screen out the worst of the flocks, and we could turn on and turn off the screen, and they would get a radically different sheet. So you can take these hand sheets and you can quantify the formation goal using those sheets. Typically, the best sheet you're going to get will be from your hardwood line only. To make a tappy sheet, you have to go to a very low dilution, which you will not get to in your head box. And so that will be the best you can do. You won't even be able to do that good, but you can begin to quantify these things. You can even make tappy hand sheets by, in the lab, mixing 30% softwood with 70% hardwood or whatever ratio you want, and get hand sheets that way. It's very important to document existing machine turbulence. What does the intensity scale look like from the head box to the flat boxes? That will require a strobe light or some camera equipment, but that number needs to be documented, and how you develop the number, the scale number, the intensity number needs to be documented as well, so that others can understand what your numerical system looks like. So design the table with major emphasis on the heavyweight sheets. Speed-induced turbulence will take care of the lighter weight sheets. You can start activity with V-type blades, even on the forming board if that's required, and if your head box will allow that. If the turbulence profile coming out of the head box is very uniform, hydraulic profile coming out of the head box is very uniform, you can start your turbulence right away. If the head box has hydraulic streaks and you need to let those hydraulic streaks settle out, you can't start your turbulence until the second or third hydrofoil unit. That's why the head box is critically important, and it's important that anyone designing the foil table understand what your head box intensity looks like. So you want to increase intensity and maximize drainage for the rest of the table. Target a scale of 40 pulses per second, get as close as you can get to that. And From all this pre-work, outline what you think the table needs to look like. You may need some help there. But if you're going to buy a new foil table, one of the things that's critical is that the formation guarantee needs to be in the purchase order. And that's why you need the various handsheets to help you define that. So typical plan would be, well, first it's going to be a learning experience, and likely you're going to discover things that are pretty unique about your machine. So you may want to include in your plan writing a summary of what you've learned so that they'll be available for the next optimization effort or the next new grade. And finally, you should consider training sessions so that the learning will be more utilized in operations and not just by your technical staff, but your operating staff is critical because they have to do it every day, 24 hours a day. Let's do one quick case history before questions. There was a 30 million, this is a real case history of a real machine with these outcomes. They needed it was a 3-ply machine. There were 3 Fourdriniers. So the sheets were combined before they went to the press section. One of the plies, the middle ply, had an MB former. So there was a Fourdrinier with a top wire forming unit, an MB former. And there was a $30 million rebuild to have an improved former, an MB former on top. They spent $30 million to do this and got higher reject rates. The problem could not be immediately addressed. The problem could not be solved with the existing equipment on the foil table. It was concluded that they needed a new foil table or a different foil table. These were grades that were made as low as 1,200 feet a minute, as high as 1,800 feet a minute. So they're in a difficult forming range. And they hired a consultant, and it happened to be John Ames, a friend of mine, colleague of mine. So he went to this mill, and the first thing he did was this machine evaluation. I looked at the stock prep and everything they were doing, and of course it was a running machine, so everything was in reasonably good shape. But he took the drainage and activity profiles. And the activity profile was the turbulence was no higher than a 2. The sheet we saw before, and we'll see again, was a 6. So the optimization was increased from 2 to 6, which you'll see in the next slide. And that work lowered the rejects and increased the Sheffield smoothness by 20 to 30%. While they were doing that, the scale, in addition to the intensity going up from 2 to 6, the scale went from coarse to fine, which was a big help. Now, if you want to get all the details of what these activity profiles look like, what the Fourdrinier table looked like before and after, by the way, the optimization cost the mill about $10 million. This was not cheap. John Ames and Duran wrote an article which they published in December 2021. And this was a case history that we used, and all these profiles were shown in the booklet called Impact, Development, and Commercialization Overview of Dewatering Hydrofoils. That's available from the Tappy Press, and all the key data is on pages 36 through 39. And that is the sheet after the optimization. There are many issues which we did not touch today. We can handle some of them in the question sessions, but if you have additional questions, call or email, and I will volunteer to repeat this presentation for your organization free of charge if I can do it from home. And there are several good articles and presentations, a number we have discussed today. Again, I'd like to thank you for your participation and thank Tappy for sponsoring this series of webinars. Uh, Both Tappy and I would appreciate your feedback, and you can use the code here. And now we're ready for questions, and I'll try and back up to my slide with my contact information on it in case you want to write that down or have a question that's too long for today.
That was great, Ben. Thank you so much. So informative. We do have a couple of questions, so I'll jump right in. The first one is there a formula to calculate how much water a foil can remove?
Yes, there's a formula. If you know your sheet consistency in head box, which typically you do know, and if you know your sheet consistency going into the first flat boxes, say it's 0.5% in the head box and 3.0% going in, the formulas for the sheet consistency will give you, and if you know the flow rate in the head box, you can calculate the water removed by using those consistency equations and subtracting.
Excellent. The next question is, do the high turbulence foils help at 200 FPM?
They do, but at 200 FPM, you'll get more activity on the table, but because the vacuums developed by the hydrofoil blades are so low, you probably won't pull down the fabric and probably are not getting turbulence on the table and probably cannot get turbulence on the table. So the V blades will help. There's a question of will they help enough? And I don't know the answer to that, but I do know that formation showers will be a big help. Dandy roll will be a big help. And if your machine has a shake, optimizing the shake, getting it to the proper shake number, which incidentally is pretty close to 40, but there are articles which tell you how to calculate the shake number and have some case histories about what's a good shake number written by Dan Manson. I would recommend you look at those if you have shake and want to optimize it.
Ben, you stated that you don't recommend formation showers because of plugging issues, but with newer shower technologies like brush showers with automatic operation and timing, could this be a good option to help?
Yes. And I'll recommend the formation showers. The operating folks may have an issue with them.
Okay. Do we have any method to calculate the jet contraction ratio?
I'm not sure what's meant by jet contraction. There are formulas to calculate L over B ratios. Of course, you know what the wear speed is, and there are instruments that can be put in the head box that will give you the velocity of the jet coming out of the head box. And there are hydraulic equations which will measure other things, but I'm not sure what jet contraction means.
Okay, if the attendee would like to re-ask that question, we'll get to it when you do. What is the ideal location when jet hit the first forming foil?
There is no generalized ideal location. It depends on your head box and how uniform the jet, how hydraulically uniform the jet is. if the jet is very uniform and you can start dewatering immediately, you want to land the jet on the forming board in a way that the leading blade of the forming board begins to dewater the sheet. So that sort of makes intimate contact between the jet and the wire if it's placed on there so that you're getting a small amount of dewatering by the leading edge of the first blade on the forming board. If your hydraulic conditions are such that you would set streaks in the sheet if you dewatered immediately, then you need to land the jet on in the middle of the first blade of the forming board such that no dewatering occurs. There's some bounce from the jet off the first blade, and that will help add hydraulic uniformity to the sheet.
Okay, thank you. Next question. What is the mathematical way to set hydrofoils?
I'm sorry I didn't get all of the maximum.
What is the mathematical way to set hydrofoils?
The mathematical way is to calculate the accelerations that is created by how much the fabric runs down the nip and how quickly you want it to return to the nip. That's a mathematical issue that took John about 10 years to work out. I think he's willing to share the results and the method he used, but I don't think he's willing to give his program away. He's got this all programmed so he can just plug in certain parameters and it generates the data that you're requesting. I think he'll tell you what formulas he used and how he did that.
Have you seen formation improvements with breast roll shakes at high speeds?
I've never seen anybody, the answer is maybe. I've seen it up to about 1,200 feet a minute, but not higher, because you can't get the scale of shake that you want to achieve. You can't get 40 shakes. You can't get 40 hertz at really high speeds. I've never seen a shake over 1,200, and I've only seen one or two at 1,200.
Ben, going back to the mathematical way to set hydrofoils and John's template formula for that, he did mention in the chat that TAPI has formulas for calculating jet characteristics, including contraction. So I guess that's TAPI has those formulas for the ways to set hydrofoils.
Okay, I'm not familiar with that document. I'll immediately after today, I'll go look it up.
Yeah, thank you for that, John. Okay, the next question, Ben, is how do we change the vacuum level from low vac to high vac along the Fourdrinier?
The rule of thumb, there are always exceptions, but the rule of thumb is that you want to, for applied vacuum, not vacuum generated by the wire where you have little control over that. The only control over that is the best control over that's the angle of the foil. You want lower vacuums, use lower foil angles. But when you start adding applied vacuum, you want to first apply the lowest vacuum that that you intend to use on your first vacuum unit, say 6 inches of water, then the second unit would be higher, 8 inches of water, and the highest low vac then on the third unit would be 10 inches of water. So you want to go low vac to high vac as you go down the table. If you start out with high vac, you can take out so much water that the fines will rush to the holes in the sheet, the fine pores in the sheet, and perhaps plug the sheet and retard the drainage of the second or third unit.
Thank you. We have a couple more questions. One was, where are we taking questions? And it's in the chat and in the Q&A. So if you have any additional questions, we've got about 5 more minutes. I have some more to go through. So add your questions if you have them. Ben, is there anything in formation forming that contributes to shiners in the sheet? Shiners are in quotes.
Yeah. I want to say no, but there may be an unusual condition in some mill or some location where the specific gravities of the shiners are different than the specific gravity of the other fibers. And they might float or sink. And if they're floating or sinking, you would do different things, but typically the answer would be no.
How formation should be adjusted for recycled paper used as fluting compared to liner?
Please repeat the question so I get it all.
Certainly. How should formation be adjusted for recycled paper used as fluting compared to liner?
I think the same principles apply. If recycled paper typically has more fines, lower freeness, and therefore it's harder to drain. So typically you're going to need more agitation on corrugating than you are on virgin liner or even liner with some recycled content. And if these are being done on the same machine, you would probably want to change the foil arrangements, and you can find a table where you could change 5 or 6 blades to go to increase, particularly getting these V blades early in the table somewhere. That turbulence may be too much for liner board, but might not even be enough for the fluting. So you would want to insert some turbulence blades when you switch to fluting on the same machine.
Do you know any sensors that can measure the sheet solids on the Fourdrinier?
I believe there are. I'd have to, and they're probably not applicable on the wet end where there's a lot of turbulence, but these instruments are, and I haven't used one, but their instruments are likely have the capability to measure sheet consistency going into flat boxes. I'd have to check with the instrument people to see what they recommend.
Which equipment is the MB former?
Pardon?
Which equipment is the MB former?
The MB former is it's the Voith version. This is very a crude definition. It's the Voith version of a Bell bond. A bell bond is a unit that you would put on a machine just before the flat boxes to dramatically reorient the flocks in the sheet, or dramatically change the characteristics of the sheet, and to also dewater the sheet both upward and downward as the sheet goes through the unit. So it's like a bell bond. It's the Voith version of a bell bond, and Voith would probably tell you how the MB unit is really much superior to the bell bond unit, and I'll let them do that definition.
Okay, we have 4 more questions if anyone would like to, if anybody would like to ask any more. You can see Ben's email address right here on the screen. And the presentation will be available at ontappy.org after this webinar. Okay, Ben, how important is impingement angle and cut through distance from the forming board?
It's very critical. The angle will first, on high-speed machines, that sheet is coming out of the water, stock is coming out of the head box at very high speeds, and the amount that is going to go through the fabric is highly dependent on the angle. I have seen machines where a third of the water removed on the whole Fourdrinier table comes out immediately. It's hard to measure. You can't get typical way to get sheet consistencies is to blow stock off the wire and take it to the lab and measure it. There's so much activity in the area, it's really hard to get sheet samples. But a third of the total drainage was occurring over the forming board. And most of it is occurring at that impingement angle. That's a lot of sheet, a lot of water to remove. And this particular machine where I saw that high amount of water removed was creating some issues with the sheet, and they had to reduce that. It's easy to reduce, but then the table had to be designed to get the rest of it out. But it's very important, very critical.
Ben, will you be at TappyCon?
I right now do not have plans to go to TappyCon this year.
What is the best way to get jet wire ratio?
Well, the wire speed you have in the control rooms, it's usually quite accurate. There are instruments for the head box to give you the velocity coming out, but it can also be calculated. If you know the pressure in the head box, there's an equation where you can convert that pressure into machine speed or velocity of the jet coming out of the head box.
Okay, couple more questions if you have time, Ben, if everybody would like to stay on. We have a couple more questions.
I have,
Are you good, Ben?
I'm good.
Okay. How are the formation bubbles formed when making heavy cover weights? And what can be done to eliminate the bubbles?
The bubbles are typically related to air in the head box and are typically related to dissolved air. So air can be in the head box and in the sheet in 2 ways. It can be entrapped as air, or it can be dissolved in air. There are 2 contents to be known. And the slurry in the head box is under pressure. So there'll be more dissolved air in the sheet. When the sheet comes out of the head box and it's under atmospheric pressure, some of the dissolved air will undissolve and cause a bubble in the sheet. And so the measurements to be taken are what's the percent dissolved air and what's the percent undissolved air, and 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 there are techniques to determine those numbers, and then what can be done to reduce both of them so that there's fewer bubbles in the sheet.
Okay, what would be the maximum percent ratio of broke to avoid formation and drainage problems?
Um,
Would you like me to repeat that?
yeah, no, I understand the question. It's the answer I'm struggling with.
Oh.
Well, of course, in a recycled sheet, it's 100% broke. So it's not just the content, but it's what you do to the broke, and what you can do, and what you must do with the broke. Uh, it, it, it it's sort of an issue about what it's worth to you to use the fiber, because you're going to have to put equipment in the broke line to to first hydropulp it and potentially deflock. And if that doesn't work, refine, which you really don't want to go that far, but you may have to. And um, and the maximum percent is going to depend on how much of that you can afford to do. Um, a lot of mills that say, for example, a linerboard mill, which has linerboard machines and a corrugating machine. I've even seen broke diverted to the corrugating machine where formation is less important, and the equipment prior to the head box to break up the flocks is um, they have more equipment to do that, and so that certain percentage of the broke will be diverted to the corrugating machines. There's sort of no limit. It's just a question of how much you can afford to spend to deflock the broke. And if you have also machines with, say, for example, wet strength resin, and this is prevalent in the tissue industry, and you have broke, there'll be converting broke, there'll be machine broke. Machine broke's different than converting broke, because in machine broke, the wet strength resin hasn't cured yet. Converting broke, the wet strength resin will have cured, and so you'll have to have a chemical step in your broke line to get rid of or to take care of some of these bonding agents, and to make sure those bonding agents are neutralized so you can liberate the fibers from one another.
Okay, so two additional questions or comments more. So the one, and Ben, if you don't know this answer, perhaps John Ames can pop it into the chat. The question is, how do we get the 82 slide John Ames presentation?
John has condensed that to a 28 slide presentation. And if you will send me an email, I will attach it and send it back to you and copy John, so you and John can talk about that.
Wonderful. And Tom Redensel has been kind enough to offer to answer any fundamentals of formation questions you all may have. He will be at TappyCon, and that's Tom Redensel. You can see his name on this page.
Thank you very much, Tom. Appreciate the help.
Um, And there will be also at TappyCon a papermaking specialists subcommittee meeting. It happens early in the morning on Tuesday morning, and that's a great session to attend for problem solving. If you have any. Well, Ben, thank you so much for this informative presentations. And if anyone has any other questions, please contact Ben. As you can see, his information is right here. Again, thank you all for attending, and this webinar will be posted to tappy.org, and you'll receive an email once the webinar is available. Thank you all for your time today, and this concludes our webinar.
Thank you.
Thank you.